Welcome, chemistry students. You are welcome to the second semester chemistry course, General and Inorganic Chemistry. Unit 3 of this course is on the covalent bond, and the present chapter, chapter 3.3, is on understanding molecular geometries, the VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. The present chapter is concerned with understanding molecular geometries or predicting molecular geometries based on the postulates of the valence shell electron pair repulsion theory. Now, so far in unit 3, that is the covalent bond, we have learnt about drawing Lewis structures, calculating the formal charge, valence bond theory, concept of hybridization. Now we move further and learn about the VSEPR theory. The instructor for this chapter is Dr. P. Sharada, selection grade lecturer in chemistry, St. Joseph's College for Women, Autonomous, Visakhapatnam. Learning outcomes. By the end of this chapter, the learner would be able to comprehend the scope of VSEPR theory, understand the order of electron repulsions, predict molecular geometries based on repulsive interactions in the valence shell of the central atom, and also realize VSEPR theory limitations. So, the purpose or the expected outcomes from this chapter are: you will know the scope of VSEPR theory, you will also understand the order of repulsions between lone pair, lone pair, bond pair, and bond pair, bond pair. You will also be able to predict molecular geometries based on the repulsive interactions between electron pairs in the valence shell of the central atom. And finally, you will also be able to realize the limitations of VSEPR theory. Understanding molecular geometries, the VSEPR theory. The contents of this chapter are drawbacks of octet theory and theory of hybridization, introduction to VSEPR theory, steps to predict molecular geometries, some indicative examples, and finally limitations of VSEPR theory. Let us quickly recapitulate what we have learnt so far. In this chapter on the covalent bond, we have learnt about covalent bonding. Basically, covalent bonding involves the sharing of electron pairs, one or more electron pairs between the bonded atoms. And the purpose of covalent bonding is to attain stability. Then we have also learnt to draw the Lewis dot structures. See, electron pairs are shared between atoms, but if you want to show how the electrons are distributed in the valence shells of all the atoms that are there in the molecule, we make use of the Lewis structure. So, the Lewis dot structures are used to depict electron distribution in molecules. They focus only on the electron distribution in the valence shell of the bonded atoms. Here some examples are also shown about the Lewis dot structures. Of course, we have also learnt about the concept of hybridization, which is basically mixing of atomic orbitals of almost same energy to form equal number of identical orbitals with definite orientations. When the hybrid orbitals are oriented at a particular angle in a particular direction, then automatically the molecule also will have a similar geometry, a particular geometry which is matching with the orientation of the hybrid orbitals of the central atom. So, in this chapter, so far we have learnt about covalent bonding, which is about sharing of electron pairs. You can see here how electron pairs are shared, and both the atoms A and B have acquired the octet. You can see here the Lewis dot structures. SO2, sulfur is having one lone pair, oxygen is having two lone pairs, this oxygen is having two lone pairs, and sulfur and oxygen are having two bond pairs each between them. You can see the water molecule. So we have here we have shown how the electrons are distributed in the valence shells of the atoms that are bound by a covalent bond, that are bound through covalent bonding. It need not be a single bond, but that are bound through covalent bonding. You can also see the hybridization depicted here. There is one s orbital, there is one p orbital. So this is sp hybridization, and because two orbitals are participating in hybridization, you got two hybrid orbitals, and the two hybrid orbitals overlap with the p orbitals of the two chlorine atoms, so as to form the beryllium chloride linear molecule. So through hybridization we have learnt how to predict sp hybridization of the central atom leads to linear geometry. sp2 hybridization, plane trigonal geometry. sp3 tetrahedral. So more or less, by knowing about the hybridization of the central atom, we have learned to predict molecular geometries and also the bond angles. Now we move further and see, in some ways these theories that we have learned so far are unable to explain certain properties or certain structural features that we find later in this particular chapter. Lewis structures fail to explain bonding and shapes of molecules. What is the main drawback of Lewis structures? They only focus on the satisfying the octet rule and distributing all the valence electrons. They focus only on that, but Lewis structures will not tell us anything about the nature of bonding as well as the shapes of molecules. You can only say, you can only say two pairs of electrons are shared, or one pair is shared, two lone pairs, one bond pair. Only that much information is available, but direction of bonding or shapes of molecules is not explained by the Lewis structures. Octet theory. Of course, the Lewis structures are written based on the guiding principle of octet number of electrons, but this theory also could not explain shapes and stabilities of molecules. Octet theory does not explain the shapes of molecules. Of course, to a certain extent, if the valence shell is having an octet of electrons or an octet configuration, it is stable, but there are several examples where the molecules are stable, but the central atom does not have an octet of electrons. There are some examples where the number of electrons are less than octet. There are certain other examples where the number of electrons is greater than an octet. Now, what about hybridization? Hybridization to a large extent could account for many of the structural features as well as the reactions as well as the chemical and physical properties, but deviation in bond angles could not be explained by the concept of hybridization. For example, in ammonia, nitrogen undergoes sp3 hybridization, but the bond angle is not 109.5 degrees, it is only 107 degrees. Why? Hybridization is saying nitrogen is undergoing sp3 hybridization, so tetrahedral bond angle has to be there, but the bond angle is less than tetrahedral bond angle. This fact could not be explained by the hybridization concept. So the VSEPR theory tries to bridge these small gaps, or it tries to address these limitations and account for the deviation in the bond angles that has been noticed in certain examples. For example, you can see here water undergoes sp3 hybridization. Supposed bond angle is 109.5. But what is the bond angle mentioned here? You can see supposed bond angle is 105 in water, but it is only 104. If you see the ammonia molecule, you can see the bond angle is only 107. If you see the SO2 molecule, it has to be sp2 hybridization 120, but the bond angle is less than 120. So, in order to account for these anomalies, the VSEPR theory has been proposed. VSEPR theory, which is valence shell electron pair repulsion theory, predicts molecular geometry based on the electron pair distribution in the valence shell of the central atom. See, name itself is indicating this theory is focused only on the valence shell. Point number one. valence shell of the central atom only, point number 2. Number 3 is it is pertaining only to electron pairs that are present in the valence shell. So, it is concerned with the repulsive interactions between electron pairs in the valence shell of the central atom. So, and because of repulsive interactions, when somebody is repelling someone else, automatically they try to maintain maximum distance. So, by arranging the electrons at maximum distance, you can see here there are two electron pairs here. A is bonded to two X atoms. So, there is one pair of electrons here, there is another pair of electrons here. So, these two pairs of electrons keep maximum distance from one another at 180 degrees. Supposing there are three pairs of electrons in the valence shell of A, the three pairs arrange at a distance of 120 degrees from one another. But if you see here, this particular A is also bonded to two X and two bond pairs, but because this A is having two lone pairs also, now there is a bent, the bond angle is bent, that is it is less than 180 degrees. You can see here there is a bending, or there is a reduction in the bond angle because of repulsions between the lone pairs and also the lone pair and the bond pair. So, the valence shell electron pair repulsion theory is basically focused on explaining molecular geometries and deviations in bond angles based on the repulsive interactions between electron pairs in the valence shell of the central atom. Now, let us see, here some examples are shown. So, this original concept was proposed by Sidgwick and Powell in 1940. They tried to explain molecular shapes based on repulsive interactions. Of course, the Sidgwick-Powell theory was further developed by Nyholm and Gillespie in 1957. They gave the present form of the theory, and VSEPR theory predicts molecular geometry based on electron pair distribution and their repulsive interactions. You can see here electron pair distribution in the valence shell of the central atom. Central atom valence shell is considered as a sphere. The valence shell of the central atom is considered as a sphere, and in this sphere electron pairs are considered to be localized as electron domains. So, molecular geometry will pertain to how many pairs of electrons or how many electron domains are there and how they are distributed in this particular sphere, which is the valence shell of the central atom. Now, shape of molecules depends on number of electron pairs, which includes both lone pair and bond pair as well as their distribution in the valence shell. Electron pairs in the valence shell arrange to minimize. When there is attraction, they try to come together. Positive charge, negative charge, they have attraction, so they try to come closer. That's what we have learnt in the ionic bond. But when there are repulsive interactions between electron pairs in the valence shell, they try to get farther apart. Why they try to get farther apart? So as to minimize repulsion. Now you can see here multiple bonds. One of the salient feature of this theory is that multiple bonds are treated as a single bond with super electron pair. Suppose there is a double bond. That means there are two pairs of electrons, but still it is considered the two pairs of electrons. That means 4 electrons are considered as a super electron pair. So, this particular theory treats multiple bonds also as a single bond and the electron pair as a super electron pair. You can see here in the molecular geometries that are projected, if A is surrounded by two pairs of electrons, two bonding pairs of electrons, they arrange at 180 degrees. If A is surrounded by three bonding pairs of electrons, they arrange at a distance of 120 degrees. If there are 4 bonding pairs of electrons around A, they distribute at 109 degrees 5 minutes distance from one another. If it is, you can see here, if there are 5 pairs, then they are arranged at an angle. There are 2 now, axial bonds and equatorial bonds. Equatorial bonds are in the plane, axial bonds are above and below. So axial bonds are at an angle of 180 degrees, one axial to another axial, but axial to equatorial is 90 degrees, and within the equatorial it is only 120 degrees. If it is an octahedral, that is if there are 6 pairs of electrons around A, then the bond angle is 90 degrees. Molecular geometry is an octahedron. This is linear, this is plane trigonal, this is tetrahedral, this is trigonal bipyramidal, and this is an octahedron. Applicable to all the resonance structures. Just as we said, Lewis structures can be drawn for all the canonical forms or all the resonance structures. You get resonance structures from Lewis structures only actually. So this theory is applicable to all the resonance structures that are possible. Now let us see the postulates already we have learned. Just quickly let us see for polyatomic molecules, that is if there are only 2 atoms, it's a diatomic molecule, then there is no doubt it is going to be a linear molecule only. But for polyatomic molecules with greater than 3 atoms, number of electron pairs, that is lone pair plus bond pair in the valence shell of the central atom determine molecular geometry. Electron pairs minimize repulsion by maximizing distance between themselves. Then the order of repulsion. Now let us see the order of repulsion. Lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. So what is the order of repulsions? Lone pair greater than lone pair bond pair, which is greater than bond pair repulsion. You can see in this picture that is projected, see lone pair is like a big hat, you know, ammonia molecule is shown here. Above nitrogen, on top of nitrogen, there is one lone pair. See, lone pair is occupying so much space, you know, because lone pair of electrons are under the influence of one single nucleus. They occupy a large volume. They occupy a lot of space. You can see the blue region is the region occupied by lone pair itself. The remaining, you know, there are 3 bond pairs. So the 3 bond pairs are pressed closer, and that is why there is a reduction in bond angle. Nitrogen is here, the 3 hydrogens are here. These are the 3 bond pairs. Bond pairs are pressed closer. This is the zone, you know, bond pair zone. And bond pair zone, 3 bond pairs are occupying so much less space, whereas one single lone pair is occupying so much space. So lone pair repulsion is greatest. This is followed by lone pair bond pair repulsion. You know, this is lone pair, this is bond pair, lone pair bond pair repulsion, and minimum repulsion is between bond pair. Why? Because bond pairs are under the attractive influence of 2 nuclei. Repulsion will be minimum between the bonding pairs of electrons. Bond pair repulsions are minimal. Then presence of only bonding pairs will impart regular geometry, symmetrical geometry, regular shape. If the central atom is having only bond pairs, it will give a regular shape or a symmetrical geometry to the particular molecule. Then presence of lone pairs, we have been learning, you know, hybridization could not explain. sp3 hybridization is there in oxygen of water, but bond angle is only 104, it has to be 109. Why is the deviation? Hybridization concept could not explain. Now we are getting the answer. If there are only bonding pairs if there are only bonding pairs on the central atom, no deviation in bond angles. Perfect bond angles you will get. Tetrahedral bond angle 109 degrees. That is why CH4 carbon is the central atom, no lone pairs, so 109.5 degrees bond angle is maintained. But if there are lone pairs on the central atom, there will be deviation in bond angle due to distortion in molecular geometry. Molecular geometry is distorted and there will be some deviation from the expected bond angle in the particular molecule. Now let us see order of electron pair repulsions. This already I explained. See, lone pair repulsion greater than lone pair bond pair, which is greater than bond pair. This is ammonia, only one lone pair. So 3 bond pairs are pressed closer. You can see red lines are bond pairs. The violet ball or the purple colored ball is the lone pair. Lone pair is occupying a lot of space. So bond pairs are pressed closer, less than 109 degrees. Bond angle is only 107. You can see here water. Oxygen is the central atom. Oxygen is having 2 lone pairs here. 2 lone pairs repel one another. Lone pair will repel bond pair also. That means there are 2 repulsions. Lone pair, bond pair. The minimal repulsion is between bond pair. So bond pairs are pressed closer, even closer. So here it is due to one lone pair. Bond angle reduction is from 109 to 107. Here bond angle reduction is from 109 to 104. That is further reduction, and molecular geometry is only angular. Now let us see the steps to predict molecular geometry. All this we have seen. Linear, if there are 2 bond pairs. We are speaking only of bond pairs, no lone pairs. Only 2 bond pairs means molecule is linear, bond angle is 180. 3 bond pairs, then molecular is trigonal planar, 120 degrees. By lone pairs or bond pairs, we are referring only to the valence shell of the central atom. We are referring to the valence shell and the number of electron pairs in the valence shell of the central atom only. First we draw the Lewis structure. Already we have learnt how to draw Lewis structures. So draw the Lewis structure of the molecule or ion. Arrange electron pairs around central atom with maximum separation. So after drawing Lewis structures, central atom electron pairs have to be arranged with maximum separation and assign A, X, N, E, M. A is the central atom, X is the bonded atom, Xn will refer to the number of bonded atoms, Em will refer to the number of lone pairs of electrons. E will refer to lone pair. X will refer to bonded atom or the bonding pairs. Now you can see A is the central atom, N is the number of bonded atoms, which is X, and M is number of lone pairs of electrons in the valence shell. Then you identify molecular geometry based on lone pair, bond pair, and bond pair repulsive interactions, and then predict the bond angles. Here you can see when there are no lone pairs, geometries are regular. The molecule will have a regular geometry and bond angles are also perfect. You can notice the bond angles in the molecules. There is no deviation from the expected. So far in this video, we have learnt about the postulates of VSEPR theory and the applicability of the theory in respect of molecules where the central atom does not have any lone pairs of electrons, where the molecular geometry is regular and where the bond angles are just as predicted. In the following video, we will learn about molecular geometries where the central atom contains one or more lone pairs of electrons. We stop here. Thank you. All the images in this video are adapted from open source website on the internet. Thank you. Welcome back, chemistry students. We continue with our VSEPR theory. VSEPR theory is valence shell electron pair repulsion theory. In the part 1 of this chapter, we have learnt about the postulates of VSEPR theory, steps to predict molecular geometries for molecules where the central atom does not contain any lone pairs of electrons. We proceed further now to VSEPR theory part 2, wherein we will learn about predicting molecular geometries in the case of molecules where the central atom contains one or more lone pairs of electrons along with bonding pairs of electrons. Bond angle. Now let us see the molecular geometry with electron pairs in valence shell. Suppose there are lone pairs. Suppose the molecule is having lone pair. You can see the first case here, two pairs of electrons in the valence shell of the central atom. Molecule is linear. There are only two pairs, no scope for, there are only two pairs and both the pairs are bond pairs. So there is no deviation in bond angle is 180. Supposing there are three pairs, all the three are bonding pairs. Molecule is trigonal planar. But of the three, two are bonding pairs and one is a lone pair, then it is bent. It's plain trigonal here. It is bent. You are not having the third atom, no? When you don't have the third atom, in the third atom place you are only having a lone pair of electrons, molecule is bent. Supposing you are having four pairs of electrons. If there are no lone pairs, it is tetrahedral. If there is one bonding pair, like in the case of ammonia, it is pyramidal. You can see here tetrahedral, it is pyramidal. Like ammonia, nitrogen will have one lone pair, the remaining three are bond pairs, molecule will be trigonal pyramidal. Supposing like in water, you are having two lone pairs. Water is having oxygen with two lone pairs. If there are two lone pairs, molecule is bent. So no lone pairs, tetrahedral. One lone pair, trigonal pyramidal, and two lone pairs, it is a bent molecule. Supposing there are five pairs in the valence shell of the central atom, then if there are no lone pairs, it is trigonal bipyramidal. If there is one lone pair, it is a seesaw. Seesaw, you know the seesaw, children will play seesaw, it is of that shape. Then you have the T shape if there are two lone pairs. If there are two lone pairs, the green balls above and below, you can see here. If there are two lone pairs, it is T-shaped. And if there are three lone pairs, it is simply a linear molecule. If there are three lone pairs, see lone pairs are shown with blue. You can see three lone pairs in the equatorial plane, molecule is linear. Here there are two lone pairs in the equatorial plane, molecule is T-shaped. Green balls are the atoms. Now you can see the last case, when there are six pairs of electrons in the valence shell of the central atom, no lone pairs, it is octahedral. One lone pair, it is square pyramidal. Lone pair is shown blue. Look here. Lone pair is shown blue. Bonded atoms are green. And if there are two lone pairs, both lone pairs in the equatorial plane, molecule is square planar. There are three lone pairs, molecule is T-shaped. There are four lone pairs, molecule is linear. Now you can see lone pairs, presence of lone pairs is causing some change in molecular geometry. Later you will also realize bond angles are also distorted. Sometimes bond angles are also, there are deviations in bond angles, molecular geometry is distorted. You can see here AX2 molecule, you can see here the example shown is BeH2. So BeH2 is having, there are two, you can see here, the central atom is beryllium here, the central atom is carbon here, molecule is linear. See, both molecules are linear. With respect to diatomic molecules, there is no problem at all, it is only linear. Even carbon dioxide is triatomic, but the molecule is linear because carbon is having no lone pairs, both the pairs are only bonding pairs. Between carbon and oxygen, here you are having two bonding pairs, here also you are having two bonding pairs. So there are no lone pairs, molecule is linear and you are having a 180-degree bond angle. Now let us see this example AX3. AX3 means there is one central atom bonded to three other atoms. Here in the example shown, boron is the central atom. There are three chlorines around it. But boron is not having any lone pairs. So when there are no lone pairs, no worry. No lone pairs means no worry. You can see here the bond angle is 120 degrees between chlorine, boron, chlorine. Chlorine, boron, chlorine, bond angle is 120 degrees, no deviation, regular geometry. Of course, let us see the next example. You can see the carbonate ion here, CO3 2 minus. CO3 2 minus means it is AX3. Here also you can see it is also there are 4 atoms in this molecule, but since carbon is not having any lone pairs, there is no deviation. Molecule is having a 120-degree bond angle between oxygen, carbon and oxygen. Of course, now let us see the next example. Next example is SO2. SO2 is also triatomic, but the outstanding feature is that sulfur is having a lone pair. When there is a lone pair, there is no atom here. See, there is supposed to be an atom. In place of an atom, you are having a lone pair. When it is having a lone pair, molecule will have actually supposed to be 120 degrees. All these bond angles are 120, but here it is less than 120. It is only 119 degrees is the bond angle due to the presence of one lone pair on the sulfur atom. So what is this case? This case is AX2E. Example, E stands for one lone pair. A is the central atom, which is sulfur. X2 is the 2 oxygens. E stands for one lone pair on the sulfur atom. Now let us see the next example. Tetrahedral AX4, one central atom, 4 other atoms. AX3E, that is one central atom, 3 other atoms and one lone pair. AX2E2, that is 2 lone pairs and 2 atoms. Let us see all those examples here, all the 3 examples. You can see the examples are methane, ammonia, water. We have already discussed these 3 examples already. Methane, there is no lone pair on carbon, so regular shape, tetrahedral shape, bond angle is 109.5. Ammonia, nitrogen is having one lone pair, so there is a deviation in bond angle, only 107. Molecular geometry is pyramidal. Water is a bent molecule, there are 2 lone pairs, bond angle is decreased even further. It is up to, it is 104 point something, it is roughly written as 105. So we have seen the case where there are AX4, AX3E, AX2E2. Now let us move further and see the case where we are having a central atom with 5 bonded atoms and 1 or more lone pairs. Whenever you are having a lone pair, it means you are getting a deviation in the expected bond angle and a distorted geometry. Now let us see here, this is we have, let us go to next slide. AX5 trigonal bipyramidal, AX4E seesaw, AX3E2 bent, AX2E3. Let us see the AX2E3 is linear. You can see here all the examples are shown. Yeah. See here is AX5, PCl5. Because phosphorus is not having any lone pairs, molecule is a regular shape, molecule is symmetrical, trigonal bipyramidal. There is no deviation. AX4E, there is one lone pair. Example is SF4. Because of this lone pair, you can see here, actually the bond angle in the equatorial plane has to be 120 degrees and the bond angle between an axial bond and an equatorial bond has to be 90 degrees. And you can see here the lone pair is placed in the equatorial region, not in the axial, not on the axial bonds. Why? Because to minimize repulsions, when the lone pair is present in the equatorial region, on an equatorial bond, the repulsions are less at 90 degrees. Repulsions at 90 degrees are less. If you place this lone pair on an axial bond, repulsions at 90 degrees will be 3. So to minimize repulsions, lone pair will be in the equatorial plane, because of which the 2 axial bonds are pressed closer. You can see the bond angle between axial bonds has to be 180. Straight line, no? Chlorine, phosphorus, it has to be 180. But this straight line is pressed. You can see the bending. You can see the bending here. Bond angle is only 173. What is supposed to be 180 is only 173. What is supposed to be 120 is only 102. So there is a distortion in molecular geometry. You can see with 2 lone pairs, both lone pairs are in the equatorial region. on equatorial bonds. These are the axial bonds, these are the equatorial bonds. So both lone pairs are on equatorial plane or in the equatorial region, because of which now you are having this F3 is like, you can see the molecule has to be a trigonal planar. You must have expected the both lone pairs to be above and below. No, it is not trigonal planar. Instead, it is a T-shaped molecule with both fluorines on axial bonds and one fluorine in the equatorial bond. So you can see the molecule is T-shaped. If you have three lone pairs on A, you can see here molecule is linear. Three lone pairs means all the three equatorial bonds are having lone pairs. Bond is not there, but the pairs of electrons are there, and the two atoms are above and below. You can see the molecule is a linear molecule with 180 degrees. Here the molecule is 90, there is 90-degree bond angle between fluorine, chlorine, fluorine, and it's a T-shaped molecule because the lone pairs are present in the equatorial region. Now let us move further. You can see here molecule is linear. I think it's visible to you. You can see fluorine, xenon, fluorine, difluoride, XeF2. You can see fluorine above, fluorine below, and the three lone pairs are in the equatorial plane only. Molecule is linear. Now let us see AX6 octahedral. With one lone pair it is square pyramidal, two lone pairs it is square planar, three lone pairs it is T-shaped, and four lone pairs it is linear. All of them are shown here. You can see lone pairs are always depicted in blue, and bond pairs or bonded atoms are depicted in green. You can see here. The examples are presented underneath. You can see SF6 is a regular octahedral with an octahedral bond angle of 90 degrees. Excepting for fluorine, sulfur, fluorine, in the axial it is 180 degrees, but rest all bond angles are FSF bond angles are 90. You can see here this is a square pyramid. You can see why, because there is one lone pair on bromine. This is a square pyramidal geometry. You can see here this is square planar. Chlorine is having two lone pairs, and these are the other two indicative. No examples, they are only shown with A and X. They are the other two indicative examples. Limitations of VSEPR theory. So far we have learnt about what is VSEPR theory, how it is accounting for distorted geometries and deviations in bond angles, how you can predict based on is it how many bonding pairs, how many lone pairs, a central atom, how are the lone pairs and bond pairs distributing themselves with minimal repulsion. The underlying fact is that they always try to reduce repulsions. When can they reduce repulsion? When they stay as far apart as possible. So based on that we can predict how many lone pairs. We saw AX2E2 or AX3E. E stands for lone pair. How many lone pairs are there? Where are they situated? Based on that we can predict molecular geometries, and we can also account for distortions in bond angles. But despite all this theory also has some limitations. This theory is not applicable to the supposing isoelectronic species. What are isoelectronic species? Isoelectronic are the species where the central atoms will have central atoms of different molecules will have same number of valence electrons. So what does our theory say? Yeah, this many number of electrons in the valence shell means it has to be distributed like this. Molecular geometry should be this and bond angle should be this. But we will notice some deviations despite being isoelectronic. The molecules will have different geometries and different bond angles. Even deviations are also different from one another. Of course there is deviation, but the deviation in one case is different from the deviation in other case. But this theory does not tell you that if you are having this many lone pairs and this many bond pairs, this will be the geometry, these are the bond angles, this can be the deviation. But why some are having less deviation, why the deviation is more in other cases despite being isoelectronic. Isoelectronic means same number of electrons in the valence shell of the central atom. in two different examples. So this theory could not account for that. This theory also is not applicable to transition metal complexes and transition metal compounds or ions. This theory is not applicable there. It cannot explain the geometries. There, there's a altogether different theories are there to explain or account for molecular geometries and structure of complex compounds. Now, it also ignores substituent influence. See, one strong drawback of this theory is that this theory is always focused only on the central atom, on the valence shell of the central atom, on the number of electron pairs of the central atom, and the types of electron pairs, the lone pairs, bond pairs, how they are distributed. Always focused only on the central atom. It doesn't take into account the substituent, that means the other atoms. What about X? See, we are saying AX4E, AX4E2. You are focused only on A. But what about X? X will have some lone pairs. X will have some overlapping orbitals with the central metal atom. So this theory ignores substituent influence at the substituent size. Some atoms may be small, so that X can be small, X can be big, X can have 2 lone pairs, 3 lone pairs, and the aspects pertaining to the substituent atoms is totally neglected in the VSEPR theory. That is the reason why it could not account for the transition metal complex compounds and does not consider orbital interactions. There can be bonding interactions. There can be pi bonding interactions. If there are overlapping orbitals, to a certain extent there can be pi bonding also. So it does not consider orbital interactions, are totally ignored. Always focused on Lewis structures, electron pair distribution, how the electron pairs are oriented. So orbital overlapping and pi bonding interactions are totally ignored. And predicted molecular geometries are only similar, not exact. You can only say T shape, but within T also, it will not tell you exactly what is the bond angle between two atoms and the central atom. You cannot, does not say XAX, what is the exact bond angle. It will only tell you geometry, roughly. They're similar. Molecules in reality are similar to predictions but not exact. Exact values cannot be obtained. And one final drawback is that halides of group 2 are alkaline earth metals. Alkaline earth metal halides are supposed to be linear, but they are bent. Despite the central atom not having lone pairs in the valence shell, these molecules are bent, which could not be accounted for by the VSEPR theory. Exact bond angles cannot be determined, only qualitative prediction. You cannot say just this deviation will be 4.5 degrees. You cannot say like that. You can only, it helps you to predict the approximate values, but exact bond angles cannot be predicted by the VSEPR theory. These are the limitations of the VSEPR theory. So in a nutshell, what have we learned so far? Covalent bonds are formed by the sharing of electron pairs, and covalent molecules and ions can be depicted through Lewis structures. Octet rule fails to explain molecular geometry, and hybridization concept cannot account for deviation in bond angles. We have also learned that VSEPR theory is useful for predicting molecular geometries based on number of electron pairs in the valence shell of the central atom. And we have also learnt that electron pairs stay as far apart as possible to minimize repulsive interactions, and the order of repulsions are lone pair repulsions greater than lone pair bond pair repulsions, which are greater than bond pair repulsions. We have also learnt presence of lone pairs on the central atom distorts molecular geometry and it results in deviation from the expected bond angle. And we have also learnt that VSEPR theory can be used only to make qualitative predictions, but exact bond angles and exact molecular geometries cannot be determined by this theory. Thank you. All the images in this video are adopted from open source websites on the internet. Thank you.